everyone, thank you so much for clicking onto the video. Today we're going to be looking at infrared spectroscopy. So first we're going to look at how it causes covalent bonds to vibrate more and absorb energy. Then we're going to look at the absorption of infrared radiation by atmospheric gases containing a carbon-oxygen double bond, an OH bond and CH bonds, the suspected link to global warming and resulting changes to energy usage. Then we're going to look at the use of an IR spectrum of an organic compound to identify an alcohol from an absorption peak of the OH bond, an aldehyde or ketone from an absorption peak of the CO double bond, and a carboxylic acid from an absorption peak of the CO bond, and a broad absorption peak of the OH bond. Then we're going to look at interpretations and predictions of an infrared spectrum of familiar or unfamiliar substances using supplied data, and then finally the use of infrared spectroscopy to monitor gases causing air pollution, and in modern breathalyzers to measure ethanol in the breath. So now we're going to talk about infrared spectroscopy. And starting with a little bit of background, all bonds will vibrate at a characteristic frequency. So it's different for different bonds. And the frequency will depend on the mass of the atoms in the bond, the bond strength, and also the type of vibration. And the frequencies at which they vibrate are in the infrared region of the electromagnetic spectrum. And if infrared light is passed through the compound, then the compound will absorb some or all of the light at the frequencies at which its bonds vibrate, and so we can kick it into a higher state of vibration. And a really important thing to know is that the infrared light is measured in wave numbers. And we define this as 1 over the frequency in centimeters. A really important part of the infrared spectrum, like the one we have down below, is this fingerprint region, and it's the thing that we have boxed in red. And this is below 1,500 centimeters to the minus 1, so that's 1,500 wave numbers. And this is the part of the spectrum which is unique for every compound, and so we can compare it with spectra of known compounds to identify it. This region can also be used to check if a compound is pure, because if a comparison of the spectrum is made to the spectra of the pure compound, then they should be exactly the same if it is pure. And one thing to note is that it's really hard to pick out functional group signals in this region, so we rarely use this to find different functional groups. However, the functional group signals will be above this 1,500 centimeters to the minus 1, and this is the part we use to spot characteristic signals for functional groups. And we have a table in our data booklet with the absorption data of different bonds. So we can use these tables along with the spectra to find out what the compound is. So now I'm going to look at how to interpret infrared spectra. Firstly, I'm going to go over two signals that it's really important to be able to distinguish between. And it's the OH group of an alcohol, which are more round like tongues, compared to OH groups of carboxylic acids, which are more wide like valleys. And we'll look a bit further into this. So firstly, looking at ethanol, this is an aldehyde. And we have this C double bond O peak that we're looking for. So we go to our table in our data booklet. So here is our C double bond O, and it says it's present in aldehydes, ketones, carboxylic acids, esters, amides, acyl chlorides, and acid anhydrides. So because aldehydes fits into this category, then we know that definitely there'll be a peak between 1,630 and 1,820 wave numbers. And this peak we have here is at about 1,700 centimeters to the minus 1. And so this must be the peak for this C double bond O. And then looking at ethanol, which is an alcohol, we have a C single bond O peak and also an OH peak. So first looking at the C single bond O, we look at our table at this row, and this says that there should be a peak between 1,000 and 1,300 centimeters to the minus 1. And so it must be this one here because it's at about 1,000. And this is how we can confirm that this particular molecule has this C single bond O. And then we can have a look at this OH group. So we have two OHs, and you have to be really careful with looking at which one you use, because we need to look at the location. And because ethanol is an alcohol, we need this OH at the bottom here. So our peak should be between 3,200 and 3,600 centimeters to the minus 1. And so this is at about 3,400 centimeters to the minus 1. 3,400. So this is well within our range of this OH bond for alcohols and phenols. So this must be an OH of an alcohol. And so using these, we can deduce that this is an alcohol. And then looking at ethanoic acid, this is a carboxylic acid. And firstly, we have the C single bond O again. So this should be again between 1,000 and 1,300. And this is at about 1,300 or 1,250. And then we have a C double bond O, like in ethanol, the aldehyde. And so again, we have a peak at 1,630 to 1,820. So this is at about 1,700. And then we have an OH group. But now it's really important to remember that the OH of an alcohol and the OH of a carboxylic acid will give different peaks. So this time we look at this peak here for this OH. And so this tells us that we should have a broad peak between 2,500 and 3,300. And this peak is at about 3,000. And so it's in this range. And then finally looking at this general spectrum, so this isn't of a particular molecule, but I just wanted to point out this CH peak that we have here. This is actually known as a CH stretch, and this just indicates that we have CH bonds. So again, we need to remember very importantly that the OH group of an acid and an OH group of an alcohol produce different peaks. So in general, the peak for an alcohol will be more tongue-shaped, so like this. This will be our alcohol. Whereas for the carboxylic acid, it'll be more broad, so a bit more wide, and also have a few more bumps. So this is our acid, our carboxylic acid. And the peak we have for an alcohol is at a much higher wave number compared to the acid. Now I'm going to talk about the greenhouse effect. So lots of the sun's visible and infrared radiation is relatively unaffected by atmospheric gases. And this radiation passes through the atmosphere to the Earth's surface, where most of it is absorbed. However, some is re-emitted from the Earth's surface as infrared radiation, which has a longer wavelength. And greenhouse gases, so for example, we have water vapor, carbon dioxide, and methane. These will all absorb this infrared radiation because it has the same frequency as the natural frequency of their bonds, so the frequency in which their bonds will vibrate. And the infrared radiation is absorbed by bonds in these gases in the same way as in an infrared spectrometer. So, for example, the carbon dioxide has two C double bond O bonds, which absorb in the infrared region of the spectrum to vibrate. And eventually, the vibrating bonds in these molecules will re-emit this energy as radiation. And this increases the temperature of the atmosphere really close to the Earth's surface. And this is what we call the greenhouse effect. And this greenhouse effect then contributes to global warming. Now I'm going to talk about the applications of infrared spectroscopy. So many pollutants can be identified by their infrared spectral fingerprints. So the fingerprint regions will be the same. And remote sensors analyze the infrared spectra of vehicle emissions to detect and measure carbon monoxide, carbon dioxide, and hydrocarbons in areas of a high vehicle density. So, for example, by a motorway. And this means that we can monitor localized pollution. So this is the first example we need to know. So the remote sensors will analyze the infrared spectra to detect and measure carbon monoxide, carbon dioxide, and also hydrocarbons. So we monitor localized pollution. And then the second example we need to know about is in breathalyzers. So what happens here is we pass a beam of infrared radiation through the captured breath in the sample chamber, and we detect the infrared absorbance of the compounds in the breath. And the characteristic bonds which are present in ethanol are detected. So the more infrared absorbed, that means the higher the reading and the more ethanol in the breath. So now I'm going to start looking at some questions. For question 1, the infrared spectra shown are those of 3 compounds. We have 1,4-dibromobutane, butane 1,4-diol, and butane dioic acid. We now need to identify the compound responsible for each spectrum using the data table in our booklet. So firstly, if we have a look at our 3 molecules. So this first one here is just a haloalkane. And then here we have a diol, so we should see OH groups for an alcohol. And this last one here is a carboxylic acid. It's actually a dicarboxylic acid, but it doesn't really matter how many COOH groups we have. And this should help us in working out which spectrum belongs to which compound. So firstly, looking at the diol, this is actually the easiest to recognize because we know that it has a peak that is quite narrow that looks like a tongue. And this should be at around 3,230 to 3,550 centimeters to the -1. And so here on this spectrum, we have this peak, and this must be an OH peak because it has that tongue shape, and also it's at about 3,400, which is in our range for the OH of an alcohol. And so our guess is that this is the butane 1,4-diol. Another thing to note is also that here we have the peak for this CH bond. But this doesn't matter as much as the OH group because this is what defines an alcohol. So we guess that this is our butane 1,4-diol. And then moving on to the dicarboxylic acid, this should also have an OH peak, but a bit of a broader one that looks more like a valley. And so we guess that it's this one on the right because here we have a peak that could be this OH peak of an acid. And using our data booklet, in the table, this OH bond should have a peak at about 2,500 to 3,000. And this is at about 3,000 or 2,900. So this must be our OH group of an acid. And so this basically already tells us that we've got a carboxylic acid because we can only have an OH part of an acid if it's a carboxylic acid because you don't know about any other acid. And so the other thing to look for is the C double bond O that we also see in a carboxylic acid. So this should give a peak at about 1,680 to 1,750 centimeters to the -1. So it must be this one here. So this is a C double bond O at about 1,700. So this tells us that this is the butane dioic acid. And then finally, moving on to the last one, we just need to confirm that this is the haloalkane. So what we see in a haloalkane is a CH bond. So it's this peak here. This is the CH stretch of an alkane. And this should be at about 2,850 to 3,300. And this is at about 3,000. So this must be our CH bond. And this is actually the only thing present in this haloalkane that is distinct in the spectrum. And so we've worked out that this is our 1,4-dibromobutane.